and welcome back to the fourth part in week 6. As promised, in this video I'm going to tell you about the three-dimensional matching problem, which is a fairly natural generalization of the two-dimensional matching problem. So the 2D matching problem is simply bipartite matching, which you have encountered before, for example, when you were looking at flows and so on. So just to recall, the matching problem on bipartite graphs is simply the following. You're given a bipartite graph with, say, bipartition AB. Remember, all the edges go across, and you're trying to find a largest collection of disjoint edges in this graph. And the perfect matching question would be, well, can we find such a collection of edges which touches every vertex, meaning every vertex is a part of one of the chosen edges. Of course, it cannot be a part of more than one of the chosen edges because it's a matching. So we would need every vertex to belong to exactly one of the chosen edges. Now, 3D matching is very similar, except that instead of a bipartition, we are thinking about a tripartition. So we bring in a third set C here. And what we are given is a collection of triplets from A cross B cross C. And it's the same question. We want to pick a selection of triplets, which is such that every element from A union B union C features in exactly one of the chosen triplets, which of course automatically forces the triplets to be disjoint as well. So that's the matching aspect of it. We want to pick a collection of disjoint triplets, but we also want every vertex in the universe, which is A union B union C, to appear in exactly one of these. So you want to cover everything, you want to remain disjoint. That's essentially the question. You could also look at an optimization version of this, and that would be a fair question as well. You're also given a target K, just like we are an independent set problem, and you want to know, is there a selection of at least K triples which are mutually disjoint? That would be the question. So I would leave it as an exercise for you to think about this variation of the question where you are trying to meet a target of at least K. But what we will be doing is we will show the perfect three-dimensional matching problem to be NP-complete by a reduction again from SAT. So as with the previous two problems, we are again going to start with 3 SAT and reduce that to 3D matching. Again, as always, let's think about this a little bit. What do we want from our reduction? We wanted to morph a formula. Again, let's say the formula is on n variables and m clauses. Right? What we want is to get a collection of triples to somehow give us a signal about an assignment. So, well, how do we do this? Well, I suppose this is a little difficult to motivate or anticipate, but I guess the idea is that we want our selection of triplets to communicate a setting of a variable, right? So if you remember, when we did the reduction from independent set, we had the edges. So we said that, well, the independent set is either going to pick this or that. And depending on what it picks, we know whether to set the variable to true or false. And similarly, when we were doing the graph coloring, we had a very similar sort of a situation where we had a vertex that was forced to a neutral color. And then, we had these edges hanging from there. And therefore, these endpoints were forced to be colored with one of the meaningful colors from which we could pull back an assignment. Now, here, we are really choosing triples. So it's not clear how a choice of triple would tell you, how to assign things. Of course, you could try to say something like, for a variable xi, perhaps we have two overlapping triples. So, for instance, we may have ai, bi, and c true, and ai, bi, c false, something like this. And well, we know that you can't pick both of these triples in your solution. You have to pick one because ai and bi are overlapping. And whatever you pick will indicate which way you're setting the variable. And I think this is an interesting idea. It's I think, a natural starting point. One immediate issue with this is that since we are looking to build a perfect three-dimensional matching, At least that's the question that we are aiming to reduce our 3-sat instance to. Whatever we pick from here, so let's say we pick this triple with the aim of setting xi to true, we'll still have to figure out how to cover the false element. So we may have to create dummy elements that can handle the coverage of the false and the true variables, because we don't know which one our solution is going to pick. So we'll have to make contingencies and provide dummy triples that can still take care of the true and the false, whichever one is not picked. But then we also have to make sure that all the dummy elements are also properly covered. So you could go down this path and try to see where it leads you. I think it's an interesting construct that might actually be workable. But I'm going to give you the sort of the textbook reduction, which is sort of in a similar spirit. We do want these overlapping triples that force you to make some choices, and those choices will dictate whether you've set a variable to true or false. So here is sort of the official construction. This is our variable gadget. This one has, it looks like sort of a wheel or a dream catcher thing with 8 spokes on it. In general, we are going to have, if we have M clauses, actually what we're going to do is create this thing with 2M spokes, and we'll sort of see why in a minute. But, what's the construction? Well, the blue stars represent elements from the first set, the green ones from the second, and the purple ones from the third. And our triplets are going to be along the solid and the dotted lines. So, for instance, this here is one of our triplets. This here is another one of our triplets, and so on and so forth. And you can see that the consecutive triplets kind of overlap at a common vertex, which means that, if you think about any selection of triplets here, you might notice that once we start picking from an odd numbered sort of a spoke here, then we are forced to only pick odd numbered triples. So we either pick all the blue triples or we pick all the red ones. But once we pick the triple that involves, the spoke labeled 1, then we cannot cover the spoke that's labeled 2 from here. We'll have to move on to 3, 5, and 7, or we could do the other way around. We could go 2, 4, 6, 8, but we cannot do both because of the overlaps at the center of this circle. But notice that whatever we do, the entire center gets covered, but it leaves the opposite parity spokes uncovered in some sense. And I think this is beautiful because it, basically gives us a sort of a hint of a signal. If I pick the odd numbered ones here, for example, then we could say that, well, that means that in some sense, we are setting our variable to either true or false. So let me just make one convention explicit so we have something to go by. So if we leave the odd tips free, let's say that means that we want to set the variable to 0 or to false. And if we leave the even tips free, on the other hand, then it means that we are setting the variable to true. So that is to say that if we cover 1, 3, 5, and 7 from here, if we pick the blue colored triples, then that means that we are setting this variable to true. But if we're doing it the other way, then we are setting it to false. So it doesn't really matter which way which way you choose to fix this convention. What is important is that once you've fixed it, you stick to it and make the rest of the construction with the clause gadgets consistent with whatever you have decided here. So as I mentioned earlier, we are introducing 2m of these spokes, where m is the number of clauses. And why are we doing that? It's just so that we have enough latching points for the clause gadgets. So now let's talk about, what the clause gadgets look like. So if we have, this being the variable gadget for say x, or maybe in particular we have, let's say x3, then, let's look at a clause which has an occurrence of either x3 or x3 bar. Now, if you have a clause which contains x3, then what we are going to do is, well, for this clause, let's say we're working with the clause cj, we're going to have, two elements, let's say one from A and one from B. That's just dedicated to representing this clause. And we're going to have this clause attached to a bunch of these folks coming from the variable gadgets. So these things here will actually coincide with the elements of the variable gadgets. And how are you going to figure out, well, what to attach to? Well, that's really quite intuitive at this point, because let's say the clause cj has x3, then we go to the x3 variable gadget and we look for the jth even tip, right? The jth even tip, not the even tip numbered j, because we have 2m of these tips, so we have m odd tips and m even tips. So just to be clear, by tips I mean the endpoints of these spokes here, the ones that still need to be covered even after we have picked the triplets from within the wheel. Like we agreed earlier, you either leave the odd set of tips free or the even set free. And we said that if you leave the even set free, well, that's when we interpret it as setting that variable to true. So if x3 has a positive occurrence in cj, then we should be able to use the clause gadget cj to steal one of the tips from here. And of course, that may not, once we have done this for all the clauses, we may not be able to cover all the tips. We'll come back to that. We're still looking for a sort of a perfect matching, but that's all right. We will return to that issue in a moment. But what I want to make sure for now is that this portion of the clause gadget can actually be covered, and the only way to cover it is to grab one of the free tips from one of the variables. But if none of the variables are set correctly, then none of these tips are going to be available for you. So then you will not have a way to cover this clause gadget. And that's at the heart of the correctness argument, which we will come to in a moment. So we're almost done. The only issue is that, well, if you count the total number of tips that we have, the tips or the spokes, as I've called them once in a while, well, how many of these do we have? We have 2m of them, one for each variable gadget. So we have 2mn of them. And well, the variable gadgets will cover half of them. So that is mn of them gone. And then the clause gadgets will cover an additional m of them, because there are m clause gadgets and each of them should be able to pick up, one of the spokes from the variable gadget. So altogether we have covered, these many. So that would be m into n plus 1 many spokes taken care of. And since we have, well, m into 2n altogether, the balanced number of spokes that need to be covered still would be m into n minus 1. So this is easily fixed. What we can do is introduce m into n minus 1 many additional dummy pairs like this. And well, we're going to have m into n minus 1 of these. They're going to be all distinct elements. And each one of these forms a triplet with all the tips, right? So we can basically clean up whatever tips are left over using these extra triples. Okay. If that didn't make sense, I would encourage you to kind of take a pause here and, really just think a little bit about, how you can take care of the leftover tips. And what I'm going to switch to now is kind of a recap argument for the equivalence of the instances that we have generated. And again, I'm going to leave this at a sort of an intuitive level. And it's really not hard to turn this into a rigorous argument. But let's start with a satisfiable 3-sat instance. So if you have a satisfiable 3-sat instance, then that's going to come with a satisfying assignment tau. So we look at what tau does to a variable x. It's going to either set it to true or false. So let's say tau of x is true. Then we go to the variable gadget for for x, and what we do is we pick up all of the blue triples here, right? All the blue highlighted triples. This leaves the even tips free. On the other hand, if tau of x happen to be false, then we'll pick up all the red ones, leaving all the odd tips free, right? Well, by free, I mean those are yet to be covered. Now, what do we do with the clause gadgets? Well, for every clause, we know that there's at least one of the literals that evaluates to true. So that means that it's compatible with the setting of at least one of these variables. So just as an example, suppose you have a clause x3, x5 bar, and x6 bar. And let's say the reason this clause is being satisfied is because tau of x5 was set to be false, right? If tau of x5 was set to be false, that means in the variable gadget, this time for x5, well, we've left all the odd tips free. And, if this was, let's say, the first clause, then that means that this element here is attached to that clause gadget, right? So we are going to take the pair of elements that represent the first clause along with this tip here. And so that's going to cover the two elements that belong to that clause gadget along with this one tip. We run through all the clauses in this fashion, we'll always find something that can sort of suitably cover it. Remember that because of the indexing, the fact that for the jth clause we are, targeting the jth odd or even tip in the respective variable gadgets, there are no clashes. We won't have, for example, if x5 is being set to false and it's satisfying, let's say 5 different clauses, those are all going to come and land on distinct tips in the variable gadget. So we're not going to have a conflict or a fight between the tips between the clause gadgets. They're all going to be nice and spread out. So each clause gadget will pick up one of these tips, and as we discussed, that's going to leave us with m into n minus 1 of the free tips that are not yet covered, and then we can use the cleanup gadgets to simply take care of those. So that tells us that if you have a satisfying assignment, then you can actually translate it into a way of finding a perfect three-dimensional matching in this reduced instance. On the other hand, if you start with the reduced instance and somebody gives you a perfect matching, well, you then have to ask, well, first of all, let's go to the variable gadgets and see how did you cover the centers of these variable gadgets. The only way to, cover the center of these wheels is to either pick up all the red triplets or all the blue triplets. That's the only way to do it. There's, if you miss out on this, then there's just no way that you cover everything at the center. So for example, you cannot pick up some mix of blue and red, because if they're disjoint, then they will leave something uncovered, and then you're going to be in trouble. It's not going to be a perfect matching. So notice that all the clause gadgets and cleanup gadgets don't touch the core of the variable gadgets. So that's the forcing in the reverse direction. You really have to pick up either all the blue ones or all the red ones. But that is our signal. So if you have picked up all the blue ones, that means that this variable should be set to false. On the other hand, if you have picked up all the red ones, then, it's the other way. If you have picked up all the blue ones, that means that you've left the even tips free. So we're going to set this variable to true. That's what we agreed on. And then if it's the other way and you picked up all the red ones, then we set the variable to false. So that was our signal. And that's the assignment that we propose. It's a valid assignment, meaning there's no ambiguity. For every variable, we know what we want to set it to. And the only thing remaining to see is that this assignment indeed satisfies all the clauses. But that it must, because suppose it's not able to satisfy a clause, that means that we would have really struggled to cover the clause gadget in our perfect three-dimensional matching. Remember that we're looking for a perfect matching, so everything must be covered. So suppose a clause CJ is not satisfied, then we ask ourselves, well, how did the core of the CJ clause gadget, how did it manage to get into the 3D matching? However it got in, it must have been because some variable is set in a fashion that satisfies the clause. There can be really no other reason. So you would have a contradiction if the assignment was not satisfying. Now, hopefully, the details of the reduction are something that you will find workoutable based on the discussion that we have had. You can find some additional commentary in the course notes, so please go and check that out when you have a chance. And that's about it. That tells us that 3D matching is as hard as satisfiability. And you might be getting a little bored at this point because all of our reductions are from 3SAT. So I'm going to leave you with one last example where we will use the fact that 3D matching is hard to show that subset sum is hard. So this will be a reduction that does not start from 3SAT, but instead starts from one of the problems that we actually showed to be as hard as 3SAT. And that will, of course, indirectly imply that subset sum is also at least as hard as 3SAT. Now, you might wonder about this a little bit because we did see a dynamic programming algorithm for subset sum some time ago. And I think I promised that we will sort of get back to that. So more about that in the next video. Thanks so much for joining me. See you next time.